we have been discussing about different network measures, right? We have so far we have looked at degree distribution, right? Why degree distribution is an important metric. We have also discussed power law, scale free property, and so on. Now we move to some of the other preliminaries of a graph. Okay, and those who have taken graph theory course, right, in the past, for them this is basically a recap, but for those who don't have any idea about the graph, right, graph theory or whatever, the foundation of a graph, then this terminologies might be interesting, and we will use these terminologies throughout the course. So in an undirected network, we will call something called adjacent, right? We will say that two nodes are called adjacent if they are linked by an edge. For example, this node in this graph G1, node 1 and 3, they are adjacent because they are connected by an edge E2, right? Two edges are called incident if they share a common endpoint, right? Say edge E2 and edge E6, they share a common endpoint 3, therefore these two edges are incident. Alright, they are called incident. So adjacent and incident, adjacent with respect to nodes, incident with respect to edges. What is called a walk, right? So walk in a network is an alternating sequence of nodes and edges where every consecutive node pair is adjacent and every consecutive edge pair is incident, right? So this is a very loose definition. Okay, we will gradually make it tight or make it more constrained, right? So what's a walk? You basically start from a particular node 3, right, and you follow edges. So from 3 you can move to 5, for example, move to 5, then move to 6, move to 3 again, move to 5 again, move to 2, move to 3 and 1 and 2 and 3 and so on. This is a walk. Okay, I mean it is not the case that you start from 3 and then you suddenly so say you start from 1 and then you suddenly move to 5. This is not possible because 1 and 5 are not directly connected, right? So in order to move to 5, you basically move from 1 to 3, then 3 to 5 and so on and so forth, right? So this is a walk. Now in the walk, as you have seen, that a node can also repeat, an edge can also repeat, right? So for example, if you start from 3, from 3 to 5, from 4, from 3, you can again move from 4 to 3, that is possible, that is allowed. From 3 to 5, you can again come to 5, so in that case node 5 will be repeated and this edge E6 will also be repeated. So walk is a very very top level definition, there is no constraint, right? And what is the length of a walk? The length of a walk is the number of edges that you have traversed through this walk, right? For example, if you if you say move from from 3 to 5 to 4 to 3, how many edges you have covered? 1, 2 and 3, right? Number of edges is the length of the walk. Okay, so now let's make it little constrained, right? So there is something called a closed walk. What is a closed walk? A closed walk is a walk whose start node and the end node are same. So you start from 3, then 5, then 4, then 3. This is a closed walk. It can also be 3, 5, 4, 3, 2, 5, 3. This is also a closed walk, right? So this is a closed walk. And what is open walk? As intuitively, right? So you can understand that in an open walk, the source node and the destination node, the final node, they are different. Okay, so you start from 3, then 5, then 4, right? Then 3, then 2, and that is all. So you start from 3 and you stop at 2. This is a closed walk. This is an open walk, right? So what is a trail? A trail, now we are again making it more constraint. So work was a very general concept. Then we said that, you know, if source node and destination node are same, then this is closed, otherwise it is open. Now I am saying that if a work has no repeated edge, then this is called a trail. Okay, there should not be any repeated edge, right? For example, you say, you know, start from 3, right, then from 3 to 5, then 4 to 3, then 2, this is a trail, because here a node gets repeated but no edges are repeated. This is a trail. Now what is a path? A path is again a work where no edge and no node will be repeated. So the one that I mentioned, 3 to 5 to 4, 3 to 2, this is not a path. Why? Because the node 3 has been repeated. So trail is constrained in terms of edges, path is constrained in terms of both nodes and edges, right? So what's a cycle? A cycle is essentially, you know, a path which is closed, right? So a path means no nodes, no edges will be repeated, and if it's a closed path, meaning the source node and the destination node should be same. Say for example, you start from 3 to 5 to 2 to 1 to 3, this is a cycle. Okay, so you see examples, you know, written on the slide. So you know, these are not that complicated. What is the distance between two nodes? The distance between a pair of nodes is the shortest path between two nodes. So remember, when I talk about the path, nodes and edges will not be repeated, right? And the length of the path would be the number of edges that you traverse through. Now between two nodes, there can be multiple paths. One can be longer, one can be shorter, right? Right? For example, between 2 to 5, you see here, you can directly move from 2 to 5 through this edge, or you can move from 2 to 3, then 3 to 5, right? So there are two paths. Which one is shortest? This one is shortest, from 2 to 5. So the distance is the shortest path between a pair of nodes. You are given a pair of nodes and you were asked to measure the distance between that pair. You will say that I will look at the shortest path and that would be my distance, right? How do you measure shortest path? There are many algorithms, Dijkstra's algorithm and so on will, those are standard algorithms that people generally use, but that's not our concern here. What's the diameter? The diameter of a network is the longest shortest path between any pair of nodes in the graph, right? A longest shortest path. So remember, longest shortest path between any pair of nodes in the network. What does it mean? So remember, diameter is a property of graph, whereas distance is a property of a pair of nodes, right? So what's the diameter? You take all pairs of nodes. Now for every pair you measure the shortest path, and then you choose that pair whose shortest path is maximum, longest among all the other pairs. Let's say you have, again, hypothetical example, 1 2 1 3 2 3 1 4 2 4, right? Shortest path is 1, between 1 3 2 4, say for example 2 and 1. These are the shortest paths. So what's the diameter of the network? Diameter is 4, the longest shortest path. Okay. What is the interpretation of a diameter? Diameter basically says that how far two nodes can reside in a particular network. Okay, right? And that's the maximum, that's the worst case scenario, the maximum distance that is possible. So whenever you take any example, or whenever you think of an application, you always need to remember that there is at least one such path, one such longest path which exists, right? It may happen that the other shortest paths are very small, say length 1, length 2, length 3, but there is a shortest path whose distance is 10, for example. Okay? So, this diameter also is useful to understand the property of a network. Let us say the diameter is small. There are two networks whose diameter is small, and there is another network whose diameter is very large, right? If the diameter is small, you can think of it as a network like a star, because in a star network you see that all these peripheral nodes have shortest path 2, because from here to here you need to traverse through this path, this particular node, right? So most of the pairs of nodes have shortest path of 2, but from this node the shortest path is 1. So the diameter is 2, right? Versus if you have a network like this is called a line graph or a chain. The longest path is from here to here. So let us say I told you that there are 5 nodes in a network. There are 2 networks, both of them have 5 nodes. One network has diameter 2, other network has diameter 4. So you can immediately understand that the network which has diameter 2 may have a star like structure, and the network which has diameter 4 has a chain like structure, okay, like this. Now let us look at average path length. What is average path length? Average path length is basically simple. You take all pairs of nodes, you take the shortest path and the corresponding length, right? You sum them up and you normalize it, right? For example, here as you see, we take all pairs of nodes, we sum them up, 4 plus 2 plus 1 plus 2 plus 1, 8, 9, 10, and we divide it by n into n minus 1 by 2. What is n into n minus 1 by 2? N into n minus 1 by 2 is the number of possible edges that can be there in a graph, right? NC2, n choose 2, right? So you normalize it by either n into n minus 1 or n into n minus 1 by 2, doesn't matter. That is the average path length, right? So the average path length for this network would be lower than a chain, okay? Diameter, average path length, both of them are network centric properties, okay? Right. Now let us move to the next property, which is called the density of a network. So a density of a network, again this is very simple. The density is essentially the number of edges present in the graph and the maximum possible edges that can be there, right? So number of edges present in the graph is mod of E, right? So mod is the cardinality of the edge set, right? And what is the possible number of edges there? It would be n into n minus 1 by 2. Now what is n? N is mod V. So mod V into mod V minus 1 by 2, right? So I am moving to the numerator. So this is the density. So if the density is high, meaning that the numerator and the denominator are kind of same, okay? Meaning that the graph is highly dense, meaning that all the nodes are connected to each other. It's like a click, a completely connected graph, right? So I mean you see this example here, right? Average path length for this particular graph, it is shown as 1.3, and network density is so if you look at this one, 1, 2, 3, 4, 5, 6, 7 edges, and how many nodes are there? There are 5 nodes, so 5 times 4 by 2, right? This is 0.7. This is kind of a very well connected graph, okay? Now let us look at another interesting property. This is called the cluster of a network. Cluster of a network is essentially groups of nodes which are densely connected to each other. Now, I am making it vague intentionally because we have a separate chapter on clusters, graph clustering, graph community detection, and there we will try to make it concrete that what do you mean by cluster. Now, for the time being, let us assume that you have right a graph like this, okay, a graph like this, and you see that this can be treated as one cluster, this can also be treated as another cluster, you can also think of it as another cluster. So, cluster you can relate it to edge density, right. You can think of subgraphs. Within a subgraph, nodes are densely connected, right. Across subgraphs, nodes are sparsely connected. So, the edge density within the induced subgraph, right, of, I hope you remember what is induced subgraph, we discussed in the first chapter, right. The edge density within the induced subgraph of a graph, if this is high, then you say that this subgraph is a cluster. Okay, we'll make it concrete in one of the chapters later. Right now, let's look at some of the properties that again node centric properties that this clustering, the nodes within a cluster generally possess. Right. Then this property is very, very important. We'll keep talking about this property in the remaining part of this lecture and the subsequent lectures as well. So, there is something called clustering coefficient. The clustering coefficient is a property of a node. What is the clustering coefficient of a node? Clustering coefficient of a node Vi is the number of edges within the neighbors, the first of neighbors of a node, divided by the possible number of edges among the first of neighbors of a node. Okay, let's look at an example. So, let's take let me draw something. Okay, let's see. Let's take this one, node U, node V. We will measure clustering coefficient for both U and V. So, for U there are two neighbors, this one and this one. Okay. So, what I will see, in the numerator I will see the number of edges, actual number of edges among the first of neighbors of U. So, these are two first of neighbors, and how many edges are there? There is only one edge. So, this would be 1 in the numerator. Denominator would be total number of possible edges between these two, among the neighbors. So, there are two nodes, the possible edges would be 2C2, which is also 1. Okay. So, the clustering coefficient of U is 1. What about V? V has 1, 2 and 3 and 4 one-hop neighbors, right. And let us look at, and remember one thing very carefully, when we calculate number of edges, we are not considering those edges which are connecting the node, the node under consideration with the neighbors. We are not considering this edge and this edge. Okay. Similarly, when we calculate clustering coefficient of V, we do not consider this edge, this one and this one. We will only consider which one? This edge. We will only consider edges which are present among the neighbors. Okay. So, how many edges are there? Only 1. And how many possible edges are there? There are 1, 2, 3, 4 neighbors, so 4C2. Right. Now, this is clustering coefficient. Now, and this is also called local clustering coefficient. I will tell you why. There is another counterpart called global clustering coefficient, but when we talk about clustering coefficient, we generally refer to local clustering coefficient. Let us try to understand the interpretation of it, right. If I say that my clustering coefficient is higher than your clustering coefficient, it means that my neighbors are highly connected. They may have high understanding among each other. Let us think of a friendship network. If my clustering coefficient is high, that means my neighbors are highly connected. Of course, I am also connected to my neighbors, that is why they are my neighbors, and my neighbors are also highly connected. So, and let us take another example, another case where, say, let us take another node like say U as a node, and your neighbors are not highly connected, therefore, your clustering coefficient is less. It indicates that I am stable because my neighbors are connected, and meaning that my neighbors have high understanding among each other due to these friendship relations. And of course, since I am also their friends, so this group as a whole, me and my neighbors, they may form a cluster. In contrast to your case, your clustering coefficient is less, meaning your neighbors are not that related, they are not friends maybe, right? So it is highly likely that gradually you also lose your interest and you move out. Okay? Using the clustering coefficient, a whole bunch of algorithms have been proposed. We will discuss another such one such algorithm in the community detection chapter. There is something called permanence, which our group proposed way back 2014. This permanence algorithm is based on the clustering coefficient notion. Okay, let's move on. The next concept is global clustering coefficient. We have discussed what is local clustering coefficient. Now we discuss what is global clustering coefficient. The idea is same. The global clustering coefficient is a property of a graph, where the local clustering coefficient is a property of a network. So you may say that it's very simple. I measure the local clustering coefficients of nodes and I take the average local clustering coefficient of all the nodes in the graph, and that would give you the global clustering coefficient. Of course, this is one way. Another way is we look at something called triplet. What is a triplet? A triplet is a substructure with 3 nodes, right? This is a triplet. This can also be a triplet. A triplet is a substructure with 3 nodes. It's a motif, right? And these 2 triplets are different. Why? Because this triplet, you see, this is not closed, but this is closed, right? This is closed. Had it been an edge like this, it would have been a closed triplet. What we see, we measure the number of closed triplet in the graph, divided by, we will then divide it by the total number of triplets, can be closed, can be open, and that would give you the clustering coefficient, global clustering coefficient of a graph. Let's take an example. Let's take this graph, right? So here you see that one triplet is 1, 2, 3, 1, 2, 3, right? Right? So of course this is a closed triplet. You can also think of from this closed triplet, you can actually derive 3 triplets. Each of these triplets centered around 3 different nodes. So one can be 1, 2, 3, other can be 2, 3, 1. So here 2, 3, 1, the central node is 3. The other can be 1, 3, 2. So 1, 2, 3, 2, 1, 2, 3, 2, 2, 3, 1, and 3, 1, 2, 3, 1, 2, right? 3, 1, 2. So the center is 1. So from a triangle, a closed triplet is basically a triangle. From a triangle, you can actually derive 3 triplets centered around 3 different nodes, right? So these are 3 triplets. Let's look at other triplets. So this is another triplet, 3, 1, 4, and this is another triplet, 2, 1, 4, right? So how many triplets are there? 1, 2, 3, 4, 5. Total number of triplets is 5. How many closed triplets are there? There are 3 closed triplets. Remember, every triangle contributes to 3 closed triplets. Okay. You may also argue that, look, 2, 1, 4 is an open triplet. 4, 1, 2 can also be an open triplet. No. Why? Because you can differentiate between triplets based on the central node, the middle node. The middle node is same for both the cases. Okay. So the global clustering coefficient is 3 by 5. Okay. Now what does it mean? So number of close triplets indicates number of close friends. Now think of a graph where your global clustering coefficient is very high, meaning that you have a lot of triangles, right? Means this graph is very dense. Okay, you can infer many things from the value of the global clustering coefficient. Let's look at the last concept in this lecture, which is called connected component. Okay, what is connected component? Connected component of a graph is a component where there are nodes, of course, but nodes are connected within a component, but they are separated from another component. If a graph is disconnected, how do you know that a graph is disconnected? If there is at least one shortest path between every pair of nodes, then the graph is connected. Let's take a graph like this. This is one graph, but two components. If you take one node from here, another node from here, you will not see a shortest path of opposite finite distance, right? So this is a disconnected graph. So this is one component, this is another component. Now depending upon the notion of connectedness, you can think of two different types of components. One is called strongly connected component. In the strongly connected component, nodes are, this notion of strongly connected component and weakly connected component comes from the directionality of an edge. If you have a directed graph, right, then if you take a component and if you take a pair of nodes, and if you see a path between all pairs of nodes. Now remember, when I say that a graph is directed, say this is the direction, right? This is the direction. So from A to B, you can move through the direction of the edge, but you cannot move from B to A because the direction does not permit you. Okay? So let's take an example, a component in a directed graph where there exists a path between all pairs of nodes. So from A to B there is a path, from B to A there is a path for all pairs of nodes. Then it is a strongly connected component, meaning that you have an edge like this, you have a path like this, right. Let us take an example of this one, right, A, B, C, a cycle. This is a strongly connected component. From every node, you can move to other node through the direction. Weakly connected component, another notion, where again for a directed graph, if we forget about the directionality, for a directed graph, you think of it as an undirected graph, right? And in an undirected graph, then you take every pair, all pairs, and you see a path. If a path exists, then it is a weakly connected component. Think of this one. This is not a strongly connected component because from B you won't be able to move to A, but this is a weakly connected component because if you forget about the directionality, you can move from B to this to this to this, right? And in the next chapter, we'll talk about something called giant component. What's a giant component? Giant component in a disconnected graph, giant component is a component which constitutes 90 to 95% of nodes in a network. Think of a network like this, right? A network like this, right? And you have few other components. This is a giant component because this constitutes 90 to 95% of the nodes present in the graph. Okay? And this the concept of giant component is very important. We'll see in case of random network theory, random graph theory in the next chapter, that how giant component emerges, in the process of network evolution. So we stop here. In the next part of the lecture, which is basically is a continuation of this chapter, we'll discuss about something called centrality. It's a very important concept, right? Centrality of a node, and we'll see how we use centralities, interpret centralities for different applications, right? With this I stop here, and let's meet in the next chapter, next lecture. Thank you.